venerable algorithm that people have used in IRT for many years. The program, of course, conducts appropriate dimension reduction, such as for bifactor models or Tesla response theory models, or for two-tier models, these multidimensional models with special factor structures. And it also implements what is known as the Metropolis-Hastings-Robbins-Monroe algorithm. It's a stochastic approximation optimization approach. And those algorithms so far have been available up until version 3.51 and 3.52. So with this transition over to 3.6, we've added Markov chain Monte Carlo, and specifically a version of the blocked Metropolis approach, of course, with variations based on some of the original writings in the late 1990s, early 2000s in Markov chain, in the use of Bayesian methods such as MCMC for item response models. And those can be quite useful for high dimensional models or models with special features like models with covariates, cross-random effects, multi-level models, so on and so forth. And we handle a variety of IRT models from version 3.5 to 3.6. The bigger change has to do really with improving usability and also adding to, for example, the most general of these models is the nominal model, where we've added additional features of this nominal model capability using the latest nominal model as described by David Fisson and myself in a book chapter for the Handbook of Item Response Theory. And the program can support a variety of operational type of situations, for example, diff testing, scale setting, vertical scaling, and general alignment studies using unidimensional and multidimensional approaches. The program has been supporting a number of operational K-12 and also beyond assessment programs in the US at the very least, and also overseas. The program is able to fit multi-level models, and by multi-level models, we really mean these multi-level categorical item factor type of models for nested data. And with the latest addition, potentially cross-classified data. So the classical example, as the original authors of the HLM program or hierarchical linear modeling, as they described that you have nesting of, for example, nesting of observations with individuals in a repeated measures design, or nesting of students within classrooms and schools. And these kinds of nesting occur, or hierarchical relationship occur quite naturally in social science data. The program, since version 3.5, have been able to fit a number of diagnostic classification models. And in this latest update, we have improved upon the computation. We've also improved upon the program's user-friendliness. And the models that the DCM, the diagnostic classification models that we can fit, include classification latent variables, that is dichotomous or polytomous classifications in the latent variable space. And the program can also fit EFAs. So these are traditional exploratory factor analysis type of item factor approaches where you don't preset the structure of measurement. That is, you don't force one factor to be identified by the first 5 items and the rest of the loadings must be 0. That is, you let the program do an initial extraction and then discover the structure and do rotations. And the program can do all of this internally. You can simulate from all of the above models in flexMIRT, which of course makes it easy if you are doing research or if you use it in operational settings where you're trying to address a particular operational question that requires simulation. This can be handy. The program, in terms of the computation, is written in C++, and it takes advantage of the modern parallel computing capabilities of modern CPUs, so that for large problems, you can see some parallel speed gain. And there's a number of methods for approximating error covariance matrices, which has been one of the Achilles heels of an older generation of item response theory programs, such as multi-log, parscale, so on and so forth. And we also have put in some interesting features, such as, in certain programs, for example, especially programs that assessment programs that do adaptive testing and need to support large-scale computerized adaptive tests, it is occasionally useful to conduct what is called fixed data calibration. And the program can do that. And the program can also handle conditioning covariates, as I mentioned. This could be for a large-scale educational survey type of application, or it could be used in other settings, such as in experimental studies, where you regress latent variables on background covariates and other design factors that you may have from the specific study. The program can generate scores, which is important for many IRT applications. We can, of course, compute the classical EAPs, the MAPs, response pattern-based maximum likelihood scores are included because there is a desire for people to continue to use this, especially in operational settings. And there's, of course, this long research in terms of the use of sum score to scale score conversions. And the textbook that describes this is the 2001 Thyssen and Weiner test scoring text. And the program can implement essentially all of the approaches in there. And it can also do this for a variety of multidimensional models. Lastly, the program can generate multiple imputations. So if you consider a situation where instead of having a single score characterizing the position of the latent variable, individual latent variable, instead you would like to have imputations generated to account for the lack of complete precision or the presence of uncertainty in the prediction about individual position on latent trait, then you may wish to use multiple imputation. And this is very much akin to plausible values that people have used in the large scale educational survey space. And then the model fit statistics, obviously the program uses maximum marginal likelihood. And when it does, it generates the -2 log likelihood, the AICs and BICs as byproducts. And if feasible, that is when the contingency table is not so sparse, the program will also attempt to compute the Pearson's classical X-squared statistic or the likelihood ratio statistic. And when you do Bach-Aiken EM, the program computes a variety of M2, that is the limited information statistic based on the first and second order marginal probabilities. And those statistics have been first proposed around early 2000s by Maudy Oliveros and others, and they've proven to be quite useful in assessing model fit for categorical observed variables. Latent variable models fit to categorical data. So we compute those and the corresponding RMSCA values. We also compute something that is akin to a Tucker-Lewis index for item response theory, along with the law and factor analytic tradition. And there are a variety of diagnostic indices at the univariate and bivariate level, and at the level of sum scores for assessing latent distribution fit, and sum scores for assessing item fit. So the program, once it's done with estimation, it can save the output into PRM files. And these PRM files or parameter files, they can be quite useful if you have lots of items to manage, such as in operational settings or in perhaps a large research study, and they become convenient for subsequent interactions between the calibrations and scoring runs.